but
Yeah, as I recall, Jeremy kept saying,
well, it's taking a while to come across, but
it has to like get situated. And it'll turn green. Yeah. And this is what we want to mute this. It's muted. Okay.
yeah, hold on a second.
Where's your Zoom?
What do you mean?
Your Zoom window.
Oh, it's
Set up.
there. It is.
Yeah, let's take a peek.
Got it.
Okay. Okay. And I'll go check it.
Yeah, I'm doing it right now, but yeah, go for it. Yep.
Your Zoom window. Oh,
Yep.
And I'll check out the audio.
Yep. The audio is working.
You're on. You're good.
Yep. So one thing though, how do we put in the person? How do you?
So that's okay then. You look good.
No. The camera of the person.
We need the PIP, the picture in picture.
Yeah.
Right. So
We're gonna do that. Hi.
I get 3 minutes to say something that is helpful.
we're not up yet, but yeah.
Yes, but so you talk to Tom. It's not me. I'm sure.
Oh, okay.
I am safely out of it.
You're out of it.
Yes, I'm just.
You're never out.
Do you want to? I think share screen. Cool. Because we need to see a green outline somewhere.
Yes.
And share the extended screen, which is screen 2.
Yeah.
There you go. And now we should have a person. You have to turn green, which is good.
Yeah.
And then.
I don't know how to do the picture in picture. I see you. You're definitely being picked up. I just.
There it goes. There it goes.
Oh yeah, I see it.
That looks correct.
Good beans.
And I'll watch the comments.
Good. Good. It's crazy. Yeah, I'm probably. Yeah, so I found her. Yeah, I'm not sure Yeah, we have we all live yeah, and then you just talk now, put it on your laptop.
Yeah, go ahead and say something. Yep, it's on.
And then
Pushes in. Just go. Just 2 buttons. Forward back. That's all you did.
Where's he go? Right there? Okay. Fine.
I'm here.
Actually, let's go now.
Popcorn in my head.
Yeah, yeah, it's fine.
I don't know. That's what you do here.
I know it's not working. Did you plug the other end of this in for that?
Yeah, it's right here.
Nothing quite good right now. Is it? Oh, maybe we have to put it Let's make the. I think it's because the slides aren't up.
Slide's running right now.
Well, it's not here.
That's the first slide. That's the presentation.
Where's the? Where's his?
That's my first business slide.
You're such a look. You're really helping to have a picture. There you go, PowerPoint.
What's up? That's YouTube.
Okay. Now,
What do you aim at with that?
anyway, it's USB. So this is working.
It's Bluetooth.
Oh, no, USB.
Both.
It may be,
Both,
but
right?
it may be, but I think
So I don't know why it's not over there. Hey, Lou.
Does that have a pointer? I got a pointer.
Well, he's got.
Okay.
Okay. You got it?
December
Yeah, it's like.
We are live already.
What's up?
We're live. Go ahead and test it. Better.
Hello? 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 Can you hear me?
Faster,
Oh, good earlier.
Let's turn it up over on campus.
Hello? 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 It's all the way up right now. It's max now.
Yeah, so
Keep going. Keep test.
Test. You hear it?
Yeah.
Test. I don't hear it. Can you hear that, Barry? Can you hear what I'm saying?
He's like,
You're gonna mess with me, right? Test. Is that good? Hello? Got it pretty close.
you turned it the right way?
Whoa!
I heard that.
You heard that? Hello?
Yeah. That's max gain.
Yeah.
That's it.
That's it. Hello? You guys hear me? No.
you heard that noise.
It goes on and off. Yeah. I heard the
Yeah.
noise.
So Tom,
So the answer is no, Ken. No,
hey Tom, could you be a little bit more into the camera?
Okay.
Thank you.
Well, I can talk loudly. Any,
It was working before.
we're gonna second.
Is the switch on?
Yeah. I mean, if you tap it, it'll be loud. Just tap the microphone.
I mean, does this mic work?
That does. That's working. I'll fiddle with this.
Yeah,
Something.
yeah, just shut that one
It
off.
was working earlier, right?
Yeah. Okay.
You have to flip it all the way over. Trick.
You're being really.
I'm going to turn this back.
Smooth.
There we go. Hot mic.
Here we go. Okay, welcome everybody to the November meeting of the Delaware Valley Amateur Astronomers. My name is Tom Nolasco. I'm the vice president. I'm a substitute tonight for Jan, who couldn't be with us. And Jeremy's not here tonight either. He's in Greenbelt, Maryland. Greenbank, Maryland.
Greenbank.
And so we'll start off with going over a little bit of business information and observers talk, and then 4 different presentations by 3 individuals. This is members night. These are 2 really impressive shots of M33, the Triangulum Galaxy. The one on the left is Gary Trapezzano, and the one on the right is John's. And the orientation is a little different. One is, I think, vertically flipped from the other. But that's well presented at this time of year. It's right overhead practically when it gets dark. It's a real nice object. Tough to see around here, but really nice in a place like Cherry Springs where the sky's dark.
I looked for that galaxy for years before I found it. I knew exactly where it was, but because of
It is,
low surface
yes,
right
it's actually easier to see in binoculars than it is to a telescope
now.
in a lot of cases because you need to see this little hazy spot.
Has the 3rd worst surface brightness of any of the
Yeah, it is.
galaxies.
It is tough. Upcoming events. You have a public star party tomorrow night. Now, 2 things. It starts at 4:30 is when the people start gathering because sun sets early. And it's going to be cool, but it's going to be clear. So it's going to be on, I think. And but I think the temperature is going to be like in the lower mid-40s. Might be a little windy. So dress real warm. Warmer than you think you might have to. And you'll be comfortable. There's a Green Lane Master Plan meeting December 6th at the Green Lane Fire Hall. It would be good to have some representatives, anybody who can make that meeting. We're kind of fighting for some minor changes really to the Green Lane site, but it's kind of an uphill battle right now. On the 10th, we have a business meeting here in Radnor. Everybody's invited. And it goes over it's kind of the year-end finance type stuff, and a little bit talking about next year. Every Wednesday before the Friday meetings, we have an astrophotography workshop. It's on Zoom. Anybody can join. The topics range from very organized topics. Maybe a presenter comes in and gives a talk on a particular kind of astrophotography. But usually it's pretty much a free form kind of a deal where you can show your pictures, you can ask for help, you can start out at the very beginning, talk about cell phone photography all the way up to deep sky, multi-hour photography. It covers all those ranges. Perseid meteor shower, really good year for the Perseid meteor shower. Location for that's going to be in a sleeping bag in a lounge chair in a dark site with good horizons. That's kind of the formula. This is an interesting shower. I've seen this from my light polluted backyard. I've seen as many as 50 an hour with skies that are terrible. But I've gone out other years and I've seen like 3 an hour. It's really a little bit hit and miss there, but they're fairly bright meteors, so you can usually see them from a light polluted area. And then we have next month the auction. And the auction is now live. And we have the next meeting we have in December. We will actually have the in-house feel and touch type part of the auction. It went live a few days ago. People are bidding on different objects. There's eyepieces, telescopes, tripods, everything you can think of practically. It's got lots of electric focusers, Crayford focusers, all kinds of stuff. But the auction is going to close out, and we transition to a in-person live auction here, and that's the 15th. Yeah, it's at the 17th. I'm not sure when the next meeting is 15th or 17th. One of these dates aren't jiving, I don't think, for me. Now it's 15th. Okay, it is the 15th, and so then you can feel in touch and see if you really want to spend the money and do it. And Mike Atwell has generously agreed to be the auctioneer. A lot of good telescopes to pick up. Some vintage ones, some old classics like the old one at the bottom there, that Odyssey Dob. So keep an eye on that. Okay. Chair reports. Brian Lee.
My name is Brian Lee. Come on here. I'm the welcoming chair, and we have 7 new members this month. Ed and Gladys Dunlap, Lee Leitner, Laura Todd, Daniel Lufkis, Gina Mastrangelli, and Bill Udisher. I know Gina and Bill are here tonight, so let's give them a welcome.
Thanks, Brian. You'll mention that the dude girl. Okay.
Okay. Yeah, dues are coming due. Next
It is
month.
renewal time.
Yeah.
So
Please.
anytime now you can
Please
pay.
re-up.
You're covered till all of 24.
Yeah, if you signed up, anywhere between September and December, you're good until next December. So,
How much is it?
40 for regular membership, 60 for family, and 10 for junior, I think. I'm not mistaken.
Elections are coming up too. We're still taking nominations for officers. I think we have at least one name for each officer right now. The biggest thing we're looking for is the members at large. I think Jan's been contacting some people about it, but we need 3 names for members at large that we can put on the ballot. So if you're interested, or you can twist somebody's arm, you're interested? Okay, good. Well, send that to Jan. Just say, Jan, you want to be a member at large? You want to be a member at large, Gary? Gary's into. Okay, good. Maybe it'll be a real contest. We'll get like 6 names.
Horse race.
We're willing to be paid off their vote.
Yeah. So there's going to be the elections coming up. There's going to be an email sent out. Make sure you sign it and check it off, because there's a bylaw change too we're looking at making. So you get to vote on that. So it's important that you, even if it's just one name for a particular office, still check it off and answer the bylaw question. And I have others. I don't know if there are chairs, but Sandy wanted to make a brief announcement. So why don't you?
Hello, everyone. For those who don't know me, I'm Sandy Goodstein. Been a member of this club for many years with others here. I'm also active with the Pennsylvania Outdoor Lighting Council with Barry Johnson. And we got a little bit involved with another group that's called the Dark Skies Committee. They actually were an offshoot, I think, of the Westchester Green Team. They got together and started to get with one of the House reps. I'm probably not going to pronounce his name right. Hillis. He's in District 156 in Westchester. Well, they came up with a House Bill 1803, and Barry actually came up with a great name for it: Responsible Outdoor Lighting Control. And so the bill, I think, actually has already been brought to the floor. I don't know if they've looked to, vote on it or anything like that. But the reason I'm bringing it up is, the more support you get from your state rep to contact them and to ask them to support the bill. And I think it's one of these bills that's really important that we hopefully get a bipartisan input on it, because this is certainly not a bipartisan issue. Neither light pollution's either Democratic, Republican, or whatever political party you may belong to. So the more people they hear from, that's what makes them go that. Now, you can go online to actually see the writing in the bill. There's things in that probably do need to be improved. We tried this, Barry. How many years ago was House Bill 300? I mean, many. So this is kind of like the second attempt to try to do this on a statewide thing. it's only going to have input on the state-owned or state-funded facilities, but at least it's kind of getting your foot in the door to do something with lights. And especially, I'm sure all of you know, especially if you're into astronomy, that's why you're here, that since the LEDs are there and the way some of them are being misused for lighting up areas, it's getting worse. So if we want to be able to, go up there and see any stars down the road, I think this is important that, we get, a little bit more active about light pollution issues and hopefully maybe get our foot in the door. And once it's in the door, maybe we can even improve on what's already there. So again, it's House Bill 1803. Okay, question?
Is there any reason that anyone could possibly object to it that we might want to think about before we reach out to our representatives?
Well, I'll give you, Bill and I shared an email, and I guess, Bill, when you talked to your rep, he said something about, well, that he's contributed to, lighting, getting extra lighting for security. It's one of these issues that basically, let's be honest, probably most of these people are ignorant. And Bill, I'm sure that response was probably one of the staffers who doesn't know their A from their other thing.
Yeah, Mike, to your point, I think in general, there's an education
gap. It's like the size of the Grand Canyon.
Most people never even thought of that, right? Like, it's not an issue that's ever come across their brain. So it's like a true or false question. So like, there's no analysis. So Susan is a
Webster.
So she wrote a draft letter that I'll send over to Jeremy.
Yeah.
We'll have that.
Yeah, so we'll have more information in the newsletter. Yeah, the people from that Westchester Green team are Susan Webster. Interesting enough, she's an English professor at E-Town College. I don't know how she got connected with light pollution stuff. But the other one is Tim Lohr. I'm probably not pronouncing his name very good, but he's a physics and astronomy professor at Penn State Brandywine. So he certainly, was attuned to these things. So it's something that, nothing ventured, nothing gained, but let's try to see it. We're going to be sending out emails, like one of my responsibilities I volunteered for. Shouldn't volunteer for anything, but is I'm going to be sending stuff out to any higher institutions in Pennsylvania Science Department. Alert them about that, see if they're going to be supportive of it. Again, the more people we can get involved, maybe the better the chance we have. So just wanted to be alert and, take a look at the bill, read it. If you have any input or something, certainly, get back to us. But let's see where it goes. Okay, thanks for the time, Tom.
Thanks. Okay, just one more quick mention. We had these youth awards. We had a little ceremony last month on it. But just a reminder that we do have these DVAA Youth Awards. There's a website link on our homepage, and basically it's for the elementary and junior high as well as high school, 2 different classifications. The information needs to be in by May 1st. There's still plenty of time, so if you know any students that might be interested, if there's local schools, you're familiar with some of the teachers or their friends or neighbors, maybe suggest that they put something on a bulletin board or something to kind of get the word out. And now, we have an observing talk by our past president, Joe Lamb. So let's give Joe a hand. Yeah.
Thanks. Which
What time is it?
I think I'm okay.
is the DVAA Eclipse the one for you?
Sorry.
Which ones are yours? That's your presentation. Which one? I don't know whose presentations. Nope.
Mine's up, I think.
Yours is up. No, it's. Sorry.
Sorry.
I just don't know the name. Could you tell me the name of it?
Yeah, it was observing report.
Sorry. DVA. I don't know the name of it, so you have to tell me what the thing is.
October, Best Observer, October Observer.
Sorry, I'm not seeing it. Do you know the name of it? It is. I'm not seeing anything that says October Observing Report. I see that folder of reports, and I see this folder of reports.
You had drug it right here, I think.
Do you want to hit that? Just see what
It's
that
one of
shows.
these two.
Best November? Is that what it was?
Here it is.
Okay,
Great.
great. So, sorry.
That's right.
I was looking at the thing, couldn't figure out what you're talking about.
Hi, everybody. Talk a little bit about the near sky tonight. So we're in the middle of the parade of planets. Yes. Yeah, I guess. Thank you. So we have Saturn, of course, and still kind of down in the weeds a little bit, but getting better every year. And it's just crossing the meridian tonight around 6 o'clock. "83 days past opposition with a ring tilt of 6.8 degrees. And this is kind of Saturn's last call. Because last August, the ring tilt was 8.1 degrees. And Tom Alaska took these great shots of Saturn 1 year apart. And I believe he took these in September of 2022 and September 2023. And you can really see how those rings are closing. So the ring tilt is decreasing by 0.4 degrees per month. And on March 23rd, 2025, the ring tilt will be 0. But we won't see it. This is a shot of one of the last ring tilts, 1995. And you can see even in the Hubble Space Telescope, the rings disappeared. Another shot of that. But unfortunately, Saturn's going to be so close to the sun that we won't be able to see it. So unfortunately, we're going to miss it. But the beginning of 2026, when Saturn comes back, we're going to be seeing the south side of the rings. We're seeing the north side now. South side of the rings will be visible. Saturn's rings are so thin, and Cassini confirmed that, 10 meters to 1 kilometer wide. And that is incredibly thin. You know, that the height to width is 282,000 to 1, if you consider that they're a kilometer wide. What that means is, if we put the rings in this building, maybe like 100 feet in diameter, it would be 100 microns wide. I mean, that is really incredibly thin. That's about the width of a human hair. So just crazy. Here's this shot of Cassini, of Saturn's moons. And most of those are available to be seen in our telescopes. We have Titan, of course, at 0.8 arc seconds, and pretty large versus our moon. I think it's the largest moon in the solar system, second largest. But these moons are all visible in our telescopes. Probably a 12-inch reflector, 14-inch reflector would be necessary for the little ones, but quite a number are visible. So Jupiter is 14 days past opposition, and it crosses the meridian about 10 p.m. and declination plus 13. So it's really coming up in the world and becoming more and more visible each year. So it's a great target right now to be seen. And the moons, if you look at the moons, they're really rather bright. Callisto was, magnitude 5.7, Ganymede 4.5. If Jupiter wasn't there, they'd be visible to our eyes. Has anyone ever seen them naked eye? I think I saw one once when I was 10 years old. I was at Camp Delmont. Might have been Ganymede, I don't know. But and look at the sizes too, 1.7 arc seconds. When Mars comes to opposition the next time, it's not going to be about, I think, 15 arc seconds. So these moons are really pretty big. So the question is, can we image detail in Jupiter's moons with our equipment through lucky imaging? Here's someone who's done it. These images are all available on AstroBin. But look at the detail. That's Ganymede. Here's Callisto by a fellow by the name of Kevin Parker. Here's Europa. by someone by the name of Simone Laberge against the planet. Just crazy. Gabrielle D'Orazio, Jupiter and Io. These images are just amazing. And they're all, within the realm of our technology now. Ganymede in Stellarium. Here's the real thing. By a fellow by the name of Tom Nolasco from the DVAA. What do you think, right? Quite amazing, Tom. So can we see any detail on Jupiter's moons visually? Have we even thought about it? Here's Ganymede drawn by somebody with a 10-inch, 12-inch Newtonian reflector at 600 power. So maybe it's possible. You never know. Neptune crosses the meridian at 10 o'clock, magnitude 7.82, and right on the southern equator, and 28.9 astronomical units away. Faint. Sorry, I can't see that very well. But if you look at the Pentagon in Pisces, it is right below that. So if you're out tomorrow night at the star party, and even if you don't have a scope with GoTo, it's possible that you may be able to find this. That's how it's going to look tomorrow night. And that's an impression in the eyepiece. This is taken with an 11-inch telescope a couple months ago. And that's reflecting image through an 11-inch scope. It's 2-second exposures. And if you expose a little longer, you'll overexpose the planet, but you'll get that little moon Triton, probably. And if you stick a DSLR behind your telescope, you should be able to see that if this telescope is driven. Just a couple second exposure will show it. Finally, Uranus, located between Jupiter and the Pleiades, crosses the meridian at 10:30, magnitude 5.8. And the same thing with Uranus. If you have a DSLR, you can easily hook it up to your telescope if it's driven and capture the moons with just a couple seconds exposure. You might wonder what moons they are, but there are a lot of resources available online for you to find that. One of them is WinJuPost in the tools section. It'll show you the positions of all the moons, and you can label them, whatever. So, and tomorrow, Venus, illuminated 62%, morning sky, rises about 3:30 in the morning, and it's just past greatest western elongation, so it's visible for a long, long time. And at the beginning of civil twilight, it's going to be at 34 degrees. So, also tonight is the Leonidas shower. From Comet Temple Tuttle, there's a retro orbit, and they're the fastest meteors of any shower, 43 miles per second. That works out, I think, to about 60 or 70 kilometers per second. And they're going to drop 12 to 13 tons of material on the Earth. I don't know who figures that out. And the meteors that you'll see are from the 1767 meteor stream. And these meteors go so fast that a 10-millimeter particle that would weigh 0.5 gram will be minus 1.5 magnitude. So quite bright, about as bright as Jupiter. So peak activity is about 1 a.m. tomorrow morning. Expectation this year is for 5 to 20 per hour. And the radiant is right in the sickle of Leo, which rises, it shows at about 1 a.m. tomorrow morning. And that's an early meteor I caught earlier this week by this Frankie Lucina, who lives in Puerto Rico. So the deep sky.
Joe,
Yes.
can I ask you a question?
Yeah.
Like when we see a really bright fireball, how large of a grain would that be?
I mean, like a gram.
Gram?
Yeah.
More?
Yeah. Very, very small. And doubt that they make it to Earth and within, any other form than maybe just dust. Yeah. Delta Cephei, double star, high in the sky, and it's also a variable. And Cepheus right there. Discovered by John Goodrich to be variable. It has several components. Component A is about 2,000 times the luminosity of our sun. And B is a small spectroscopic companion with a mass of 0.2 or 1.2 the mass of the sun. We can't see it. Can't see that. And it has an orbital period of 6 years. And it has a C component of 92.6.3, and it's located 41 arc seconds away. And it is really a beautiful, beautiful double star. Has an orbital period, they think, of 330,000 years. At the eyepiece, it looks something like this. It's the best that I could manage, but this was taken with an 11-inch telescope a couple of months ago. And if you compare it to Beta Cygni, they look quite similar. It's a really powerful double. And that's Polaris, of course. It's similar looking doubles. But it's also a variable star. It was discovered to be variable in 1784 by John Goodrich. He discovered it from a window in this treasurer's house in New York, England. He also discovered algal from here, looking out the window. He was quite a story, you know, he was deaf. And he was a prolific observer. And the A component on Delta Cephei is the variable. It has a 5.4 day cycle, 1.5 days up, 4 down, and it varies from 3.5 to 4.4. It's known as a classic or type 1 Cepheid, and it's the second closest Delta Cepheid. The first one actually is Polaris. Its distance is about 887 light years, and it's so close that it's been verified by parallax from the Hubble Space Telescope and the Hipparcos telescope, which was a telescope that was launched by the European Space Agency in the 1980s. Formerly, it was a Class B star that left the main sequence, and it has expanded out layers that are 32 to 35 times the diameter of the sun. So quite a star. And the mechanism is something like this. And it all has to do with the amount of helium that's present in the atmosphere. The hydrogen depletion causes shrinkage, decreases the radius. And when the radius shrinks, the atmosphere heats up, the helium becomes ionized to helium-2, and helium-2 is opaque, so the atmosphere is opaque, the photons are trapped, temperature and pressure increase, the atmosphere expands, there's less opacity, increased radiation, the star becomes brighter, helium reverts back to elemental helium, the atmosphere cools, the pressure drops, the cycle goes all over again. And you can follow this. This is a chart that you can use, and all these are available online, to look at comparison stars and try to chart the light curve of Delta Cephei. So over 100 years ago, when you looked at celestial objects, you had no idea what the distance was for any of them. This is a line out of William Henry Smith. He's quoting William Herschel. He says, M31 is the closest object, nearest of all the great nebulae. These people had a very difficult time trying to figure out distances, despite their best efforts. So even into the 1920s, the idea was that we lived in a universe of one galaxy. And that galaxy, that whole universe was only 55,000 light years in diameter, and the Earth is near the center. But the universe was starting to have cracks. First of all, it was the idea of the spiral nebulae. What were they? Where were they? They came in all shapes and sizes, and people wondered, were they stellar nurseries? Were they solar systems forming? Nobody really knew for sure. They didn't know how far they were. And then in 1912, Esther Slipher finds a large redshift in all the spiral galaxies, larger than you would see for surrounding objects. In 1917, Heber Curtis finds a nova in M31, 10 magnitudes fainter than normal. In 1918, Harlow Shapley finds gobulars forming a halo around the Milky Way center. We weren't near the center. This was his chart showing the sun at the vertex. 1920, Heber Curtis notes, the dust lines in M31 look a lot like the dust lines in the Milky Way. Then comes along Henrietta Leavitt. She graduates from Radcliffe and was very, very bright, very good in astronomy, very good in mathematics, but unfortunately there are almost no jobs. She joins Edward Pickering's team at Harvard and as a volunteer. And then eventually she joins for, I think, 30 cents an hour or something like that. So he eventually assigns her analysis of small Magellanic Cloud plates and large Magellanic Cloud plates to look for Cepheids and to catalog them. So this is the plot of the large Magellanic Cloud. And the plates were taken at the Boyden Station in Arequipa, Peru, sent up to Harvard, and then the people on her team and herself would analyze them. So she finds a correlation between the period and the luminosity of these Cepheid variables, and that was relatively easy for her to do because in this Magellanic Clouds, all the Cepheids are about the same distance, from the Earth. So if you knew the magnitudes of them, you probably also had an idea of the absolute magnitudes as well. And she found that the luminosity increases as the length of the light curve increases. And in a 1912 paper that was submitted for her by her boss, this is the diagram from that showing 25 variables in the small Magellanic Cloud, showing that there's almost a linear relationship. This is a logarithmic scale, but it showed a definite correlation. So Einar Hertzsprung, of the Hertzsprung HR diagram Hertzsprung, he says, geez, this is a way that we can use standard canvas to figure out the distance to all these objects. So does it work? So I did a quick comparison of three famous Cepheids, Delta Cephei, Eta Aquila, and Zeta Geminorum, and the periods are listed there, and looked up the luminosities. And the luminosities increase just as the periods do. So for those three stars, at least, the period luminosity law seems to work. So the race began to try to build telescopes to find these Cepheids and figure out the distance to these spiral galaxies and other structures in the universe. On the left is the dome of the 100-inch Hooker telescope at Mount Wilson, and it's being constructed. And in this dry run, it's actually being constructed in Chicago. It was taken apart and then shipped across the country to Los Angeles and then erected on Mount Wilson. And on the right, this is at Mount Wilson. They're building the concrete pier on which the mount for the 100-inch telescope was going to be built. So the Hooker telescope was commissioned between 1917 and 1918. And then a search began for Cepheid variables in M31. So on October 5th and 6th, 1923, 100 years ago last month, Hubble and Humason photographed M31 at the Newtonian focus of the 100-inch. It took a 45-minute exposure, and it yielded 3 suspected novae. And Hubble marked N on the novae next to each one of them. Then he went to the plate archive at Carnegie, and he looked for evidence of these from prior plates. And for the novae, he found no other prior evidence, but for one of them, he found it going back to 1909. This object showed up on other plates, and from that, he deduced that it was a Cepheid variable. So the plate was taken at the Newtonian focus. There's a shot of that on the left, and the telescope on the right. And that's the plate. And you can see on the right side, he has nova crossed out and variable. And that's a discovery photograph of V1, the first Cepheid variable discovered in the M31. And from that, he determined that M31 is 800,000 light years away, which like blew everybody out of the water. It wasn't, exactly correct, but, nobody had any idea that the universe was that big. This was just crazy, and it made big, big news. And this is David Soderblom from Space Telescope Science Institute, what he says about V1. So this is V1's light curve, and it's 30.41 days. So you would think if the period luminosity law holds, this has got to be an enormous star. How does it rate next to these other stars? So this is a modern period luminosity plot. And I plotted it on there, and it comes out to like minus 5.4, which gives a luminosity of 11,400. It's a monster star. I mean, it's just huge. I mean, extremely bright. So if you get that and use the apparent magnitude, now Hubble thought that the magnitude of the star was 18.5, but modern estimates are like 19.4. If you put it all into this equation, which measures absolute magnitude, apparent magnitude, and distance, you get 2.9 million light years. So it's not perfect, but it's in the ballpark. In the late 1940s, this was all revised somewhat when Walter Baade, who worked at Mount Wilson, discovered these population 2 stars. Population 2 stars are in the halo and in the inner disk, and they're lower luminosity and they're metal poor. And when he said that this other population existed, we've been using them, and we really should be, making, we should be allowing for that. The universe got bigger again, and the distance to M31 got to 2 million light years. So this is just another paper that came out distantly, and they're constantly revising this and adding more data to it. And so the distances are constantly changing with new information. So this is a modern image. This is Gary Trapisano's M31 that he took recently with a 76 millimeter, 85 millimeter?
Yeah.
I'm sorry, okay, 85 millimeter teleview refractor, and it is really a beautiful image. And superimposed on that is Hubble's shot. And it shows dust lanes and the star cloud, NGC 206, all which we can see pretty much in small telescopes. M32, NGC 205. Let's rotate Gary's image to match Hubble's. So now Gary's image is upside down. Let's go in a little closer. V1. I have a chart in the back of the Hodge Atlas, which is an atlas of the M31 taken with a 4 meter reflector at Kip Peak about 40 years ago. And it doesn't show V1 as well as Gary shot. So isn't that remarkable? Crazy. So if we do a weight comparison with two telescopes, you'll realize that the Hubble scope was considerably heavier. And that does include the road and the crane and the trucks. The mules, considerable difference there.
Actually, Joe, I think it weighs probably more like around 25 pounds.
Right, right. Sorry about that. Yeah, I took a little license there. So this is the modern M31. 460 kilometer clusters, at least 40 satellite galaxies, 2.5 million light years away. 5 satellite galaxies are visible visually, 3 others are visible to our cameras. Steve Gottlieb has an Excel list that lists 75 globulars visible in amateur telescopes. Alan Purdy has seen a bunch of them. That's a copy of the Hodge Atlas I have back there. They are good references for finding things within M31. So the 100-inch Hooker telescope is not doing research anymore, but it is the largest telescope that any of us can go and look through visually, and they have observing nights up there. And you know, if you're in the LA area, it certainly would be worthwhile to check it out. If you go, you won't see the Newtonian focus where V1 image is taken. That's a shot of Hubble at the Newtonian focus of that scope. And it's the largest Newtonian telescope in the world. There's never been one bigger. Palomar telescope has a parabolic mirror, but it doesn't have Newtonian focus. So the Newtonian focus there is 500 inches. But if you go to Washington, D.C., to the Air and Space Museum, it is actually there. A couple of years ago, they tracked it across country and made it part of a display. The Air and Space Museum is now undergoing a several-year renovation. You need time tickets to see. And Henrietta Leavitt, she, is denied a lot of accolades in her life, but today she is revered as just a leader in cosmology in the 20th century. And a lot of discoveries have been made because of her discoveries. So, thank you very much, everyone.
I just want to mention.
Yes.
By complete coincidence, somebody yesterday just sent me information. There is a play starting in 1 week, November 24th, about Henrietta Leavitt.
How about that?
Yeah, it's running from
around here.
Well, it's in Chestnut Hill on Germantown Avenue. It's called Stagecrafters.
Wow.
Listen, I've never been there. It's called Silent Sky. It's all about Henrietta Leavitt. And it runs from November 24th to December 10th, so you have about 2 weeks. And it also says you can get your tickets, $26 online, $30 at the door, but Thursdays only, 2 for $40 online, seniors $25. It says industry at the door, so people in the industry, that might be us.
Wow. I feel industrial.
And students $15.
Wow, how about that?
Yeah, I think they need to
check this out.
Yeah, how
It's
about
called
that?
Silent Sky at Stagecrafters.
Wow, thank you. One other thing. John Goodrick only lived to the age of 21, and he died of pneumonia. And he died of pneumonia from observing Delta Cephei. So if you go out tomorrow night to the Star Party, wear a hat. Okay, all right. Thank you.
Thank you, Joe.
Okay. So Sylvie, which one's yours? What's it called?
I think of mine. It's that one there, or mine. That one, no, that one.
23.
Okay. Good.
Mingo, you're up.
You're okay.
Hello, everyone. My name is Sylvie Stomberg. I am 15 years old, and one of the brightest stars in the nighttime sky probably isn't from the Milky Way. So I use spectroscopy to try and prove it. I don't think the clicker is going to help with that, though.
Try the.
Sorry, hold on.
We gotta put it back on.
Doing great. So one of the first things that leads to how Arcturus, can you guys hear me, by the way? Might be from a different galaxy, is that it is in a stellar moving group. Now, a stellar moving group is a group of multiple stars that have a common motion together through the galactic plane, which is basically where most of the mass of the Milky Way is kept. In the diagram on the screen, we can see the constellation Ursa Major and how it will move throughout the next 100,000 years. As we can see, there are two stars that are moving in a very different direction from the rest of them, and that's because the Ursa Major moving group keeps all the rest of the stars in the constellation together. And all of these stars have a common motion through space, except for just two of them, which is why in the diagram you can see that they move very similarly. Stars in moving groups also have very similar compositions to each other. They're made of the same things, they're around the same ages, around the same distances. But Arcturus and around 50 other stars are in a very strange moving group. Oh no.
Oh, the other button right next to it.
Oh,
There you go.
okay, we've got it to work now. Are in a strange moving group in which all of the stars are highly different from the rest of the stars in our galaxy. They're all highly metal poor. They're all moving at an extremely fast pace, and most importantly, they're not on the galactic plane, which is where the vast majority of the mass is kept. So how did this happen? The leading theory is that, well, planets have moons, stars have planets, galaxies have satellite galaxies, as the previous presenter said. So, one of these satellite galaxies had the star Arcturus and the rest of its moving group, but the Milky Way absorbed it and therefore took its stars, making this moving group move extremely fast through space. In fact, Arcturus is moving so fast that in 1 million years, we won't be able to see it by the naked eye. So, with Arcturus being in this moving group, the leading theory is that it is from another galaxy. Now, how would I prove this? Through spectroscopy. Spectroscopy is simply finding out what a star is made of, what it's composed of, based on the light that it emits, and looking at those light bands to find out more about it. Now, obviously, we can't do spectroscopy here at home, unfortunately, so I went to the University of Arizona's Advanced Astronomy Camp and got to operate the 61-inch Kuiper telescope. In using this telescope, I got to run spectroscopy on Arcturus and a few other things along with another camper. And I always wanted to go to this camp. The moment I discovered it, I applied and I got in, and we were up on Mount Lemmon for a week with Don McCarthy, great professor. He is the leader of this camp, and he kept us up at Mount Lemmon for a week with all of these telescopes, and we got to do spectroscopy. So the game plan was for me to observe 3 objects. The first being Arcturus, Alpha Boötes, and the second being a star called Edamin or Eltanin Gamma Draconis. The star is very similar to Arcturus in almost every single way. They're around the same size, they're around the same temperature, but most importantly, we know Edamin is from this area, while Arcturus we're not so sure about. And the third object we tried to go for was the Sagittarius Irregular Dwarf Galaxy, or SAGDIG. But unfortunately, that was very difficult, and we didn't quite get the spectroscopy for it. But we'll get more on that later. So the goal was to get the spectroscopy of Arcturus and compare that to Edamin. And when you get the spectroscopy of a galaxy, you can see it, and it averages out to the spectroscopy of a star. Here is what the spectroscopy of a galaxy is supposed to look like, but what me and my partner got looks more like the album cover for the latest Pink Floyd release. It didn't entirely work out, to say the very least. However, we did get the spectroscopy for Arcturus and Edamin. This was taken at the telescope. And there's some things you can immediately tell that there's a lot of differences. But the main thing we want to emphasize is that Arcturus and other stars in the Arcturus moving group are very metal poor. We can immediately see right here at 6,000 angstroms, or 10 billionths of a meter, so just a very small measurement used for spectroscopy, you can see that Edamin's sodium line is very, very deep compared to Arcturus's, proving that it has a much weaker abundance of the metal than Edamin. Over here, we can see that Edamin has a much thicker magnesium line at around 5,100 angstroms, and that Arcturus is weak in a second metal. Down here, around 4,200 angstroms, we can see that Edamin has a much thicker calcium line than Arcturus, and that it's far more defined on the slope, proving that Arcturus is weak in yet a third metal. Remember, Arcturus and Edamin are very similar stars. The only thing they really differ in is their metal content. As we can see, the rest of the graph looks very similar in shape. So what we can put together, even if we didn't get the SAGDIG spectroscopy, we can put together that Arcturus is very different from a very typical star for the red giants in our area, and there's clearly something particular about it. So in the end, even if we couldn't prove that Arcturus is from the satellite galaxy, we got a huge piece of data that could definitely help out with finding out more about that. And I got a lot of experience with the telescope, which was one of the greatest experiences of my life. And I'm going to go back to camp next year and try to expand on that. So thank you guys. Are there any questions? All right. Well, oh, yeah.
So are you implying that one of these stars was a member originally of the Sagittarius dwarf galaxy?
No, I am not implying that they were part of the Sagittarius dwarf galaxy. I'm implying that they were part of a satellite galaxy of the Milky Way that is now gone. And since the Sagittarius dwarf galaxy has a lot of metal poor stars, I just used it as an example of what the now defunct satellite galaxy could have been like.
Cool.
Thank you.
Whoa! Sorry about that.
Congratulations.
There we go.
So you want the monthly meeting one, Tom?
No,
Which one do you want?
annual eclipse. Annual eclipse. We did that one. Yeah, that one there.
Okay.
Okay, I have a short presentation on the annular eclipse. Several members provided some images that they traveled to New Mexico or Oregon or somewhere else to see the annular eclipse, and most of them, except one, is away right now. They're somewhere else and they couldn't be here tonight. So I kind of cobbled this together as a presentation of what they saw. And this was taken, there's a photo from Jan Rush at the balloon festival, kind of corresponded with the annular eclipse, which was really nice. And get these really cool balloons. There we go. So Jan and Skip went out to Albuquerque. That's right.
The place with the balloons.
Yeah, I was just testing you, so you're paying attention. And so they viewed it from the observatory of the Rio Rancho Astronomical Society, and you can see there's different club members there, but you'll see on this next slide they have these seats, and they're different. They have little punches in them. They're different from different signs of the zodiac. So during the eclipse, you got some really neat crescents on the ground formed from that. And likewise, the tiny gaps in the leaves act like little pinhole cameras, and so they were casting lots of these crescents. It was really a cool shot. And Skip took these pictures. Now he almost had a catastrophe. He had camera battery problems. He had problems with his memory card being full and getting jammed in there, and everything was going wrong, like a typical eclipse day when everything has to happen right. Nothing did, but he managed at the last minute to get things resolved, and he captured this nice sequence of eclipse images. They're taking it right through from the partial phases to annularity. And there was a sunspot. I don't know if this is Jan's sunspotter or someone else's, but
It's Jan's.
it is Jan's, okay. And but there's how annularity looked through the sunspot. These sunspotters are just a device that allow you to safely project the sun to see sunspots on a white sheet of paper. They're really good for outreach and things like that, and for schools. It's a very safe way of showing the sun. But that's really a nice little image there of that captured. Next, we have Harry and Marilyn. Marilyn went out to, they also went to Albuquerque, but he met up with the Albuquerque Astronomy Society and about 200 plus visitors at the Open Space Science Center. You can see it's pretty crowded there. They had quite a crowd. And these are Harry's quotes from his pictures that he sent me with the shadows on the building. Same thing, is similar to Jan's, but he just really liked those a lot. It's always a neat thing to look for during an eclipse if you're by a tree. And he captured this sequence of pictures. Now, this is not, this isn't actually the pictures that the camera took. This is from his cell phone taking a picture of the back of his DSLR. He had trouble with transferring the file, so he just got me these for now. But they're actually images he took of the back of the screen. And he said the temperature dropped quite a bit. Now it's 5,000 feet, low humidity, but it was definitely noticeable. And of course, annularity, crowd cheered. And he basically says it was a great experience. And there's Harry there in the middle, occupying Mars. Next, we have Mark Ferrari, and he has been out west since Labor Day, traveling around in this little teardrop camper, going to remote areas to do astrophotography. Well, he was by Four Corners area in the I think it's Bistai Badlands, I think is how it's pronounced. And so he's out there. This is the kind of camping he does. There's nobody ever seen any of his pictures, just like middle of nowhere. But he ends up meeting with these 3 guys from South Jersey group. Now he images a bit in South Jersey, so he probably knows these guys from previous, outings and stuff. But it's pretty cool, middle of nowhere. You meet up with people. That's the kind of way this hobby is. You get to know people from different places, so you get to meet up and bump into them everywhere. This is his set of images, kind of in a nutshell here, and he has a nice animation here, which I probably can only play once. So pay attention here. But this is going to be an animation here of the eclipse. But it is really pretty cool. Wow. Pretty neat, huh?
Yeah. Well, that's reverse. Right?
Mm-hmm. Yeah. And so next, we have Mike and Robin Atwell. Now, luckily, we have the Mike Atwell in the audience. And he's going to come up and just talk to his slides a little bit.
Just really quick. Hey, everybody. Yep, my wife and I were in Oregon. We were staying in Eugene. We traveled southward to get kind of into a better area of the eclipse path. We didn't camp out, but we set up at about 4 or 5 a.m. in the parking lot of a Dollar General across from the post office at Crescent, Oregon, hoping that these clouds would move on. Can you? Sorry.
Or is it? You can talk to the same slide.
Okay. Yeah. So so this was like the very beginning. You can see a little bite. Everybody had challenges, right? Our challenges were the clouds and how to manage exposures. Thick clouds, almost no clouds, things like that. And I wasn't tracking. I was just manually driving my little geared tripod head, using the DSLR at about 300 millimeter, something like that. APS-C, so seems like a little bit more than 3. So as the event progressed, I just sent this one. These are all just JPEGs. I sent to Tom. You can see the moon approaching that sunspot group like we saw earlier. And so this was like a very favorable view where there wasn't a lot of cloud, but like the next one we'll see, I think, clouds came in. It made it really dramatic and cool, but I had to, there were times where I couldn't see the image, I couldn't see the sun or the moon at all. So I would boost my ISO on my camera up to 25,000. And although I couldn't see it visually, I could capture it with the camera, which was really fantastically lucky. And so the next one, right, kind of full angularity and that's just right out of the camera with JPEGs and stuff.
It looks like it's out of a Mary Shelley novel.
Yeah, it's really very ethereal, right? Yeah. And the next one is going to be.
Oh, that's it. That's all you got. That's all you get me.
That's all I gave them. Yeah. So there, I'm done. But something I learned was just trying things in the moment. Your equipment fails, your card fails. You
at the last minute.
Take a picture of the back of your DSLR, zoom up your ISO to ridiculous levels and stuff, and and enjoy it yourself. Yeah. Enjoy it in the moment, and don't get too hung up on gear.
Mm-hmm. These are really. I really love those shots because of the clouds have such a dimension to it. It's just really neat. I think you did a great job. And last one is I didn't go out west. I went to Blodgett Mills, New York instead. If we're between Binghamton down here and Syracuse up here. And that's what I observed with. Now this, you can see, this is not 2023. This is 1994. And so I drive up. It's right off of 81. Drove up there in a couple hours. Got off of Cortland, New York. Asked the postman where a field was. He sent me 2 miles south to this Blodgett Mills. And I looked at these pictures. This is back in '94. I took these. So I was looking at these recently. I'm like, how did I park my car in the middle of the road and just sat up in the middle of the road? I think that's pretty presumptuous. I don't know. But I did. Nobody came, luckily. But here's the equipment with this really fancy solar holder here and a DSLR. This is all film back in those days, the little Bosch and Lone glass filter, just Kodachrome film. And it's a sequence of pictures similar to what you've seen. And I've been going through the sequence. I purposely picked this area to be a little bit off center. I didn't want it to be right in the dead center. I kind of wanted to go across the top. And just like in one of Mike's shots there's a little bit of a gap of light shining through from the edge of the sun, which if you're lucky, you can catch it. And then basically, it started to come out, and these storm clouds are coming up like crazy. So I took one last quick picture, threw everything back in the car, and by the time I got it back in the car, this is May, a thunderstorm comes up, and it's just pouring. But I made it by like literally seconds before the rain came. And that's it. Well,
Tom, were you shooting film? Or?
It was all film. It was film 400.
Was it print film or slide film?
Print film. Yeah. It was, so I just scanned images off the prints recently and put them up. Okay, up next is Ken, who has a couple talks, but one primary talk. I'll let him describe it.
Which one?
The eclipse one.
So bright I can't even press F5. Hold on a second, I have to bring that in.
Yeah, it looks easy.
Okay.
Is he giving us the finger?
Well, this, yeah.
That's fine. I understand. Okay. Hi, everybody. I've been a member here for about a year now, and I always enjoy listening to everything here. I thought I'd start, sometimes it'd be nice to have like a little bit of a date night here where we actually get to know each other and a little bit of our history and a little bit of our background and how did we actually get interested in astronomy. And for me, that's kind of an interesting story. My father actually worked for NASA for a while and designed, he was a metallurgist, and he designed some of the metal alloys that were used on the Gemini capsules, actually, some of the first manned flights. And that's how I got interested in space. But I was never really all that interested in astronomy as a kid, I must admit. I wasn't all that interested in telescopes, believe it or not, most of you, probably opposite of most of you. And actually, the way I got interested in astronomy was actually through my job when I worked at one of the national laboratories for the Department of Energy in my early 20s. I worked on basic energy research actually related to superconducting magnets and nuclear fusion, actually nuclear confinement fusion, which was pretty futile back then. We didn't realize how infant the field really was. If you realize 2 years ago, the Department of Energy first announced we've actually finally, after 40 years, I just looked myself, it's 40 years have passed since I worked there. They've actually achieved a net energy gain in nuclear fusion. Of course, we were able to recreate the nuclear fusion of the sun and stars as early as the development of the hydrogen bomb in the 1950s in a very destructive way. But to actually use that as an energy source and actually understand it and control it has taken this long, and yet still not clear whether it will be scalable as an energy source. So that's how I got interested. I'm actually, since retiring last year, I'm actually working as a chemistry professor at some local colleges. So I love doing these kind of things. And I also am a science education volunteer at Wallops Island in Virginia, when we lived down there in Virginia in the summers. So the presentation I'm going to give after this, I like doing these presentations. Barry and I did a presentation earlier this week that Al invited us to do an educational outreach at one of the libraries here in Conshohocken. And so I'll share this at the end. And I just want to mention that I do a lot of these kind of presentations, especially down at the NASA Visitor Center down in Virginia. This is kind of a big time for NASA right now. They call it the heliophysics big year because of the 2 eclipses. Of course, there was the annular eclipse that we just witnessed, or most of us didn't witness because we were in the rain or in the wrong location. But at least some of us, as we see, saw this nicely. But of course, the other one is coming up next April, the total eclipse, and that really made me reflect on what I learned when I worked at the Department of Energy back in the 1980s. I really knew about this, but I really didn't know about it firsthand until I actually worked in the area, of the area of nuclear fusion. So I wanted to tell you a little bit about this story, and many of you might be familiar with it, but I think it's worth recounting because it's so important to everything that we know about the energy and everything that is the source of the energy that we see by doing astronomy. So it's really the discovery of the element helium during the total solar eclipse of 1868 that's the subject that I want to talk about or recount tonight. So again, we're going to get a very similar solar eclipse here across the continental U.S. in April of next year. So before we go there, I should say that my interest in astronomy is probably a little less than my interest in astrochemistry. Astrochemistry is really a subfield of chemistry and physics, kind of highly correlated with the area of nuclear chemistry, which I kind of worked in. So what I wanted to reflect on, first of all, is, and I think you're probably aware of this, but it's good reflecting back on this fact that our sun and every other star in our Milky Way galaxy and further everywhere else in the universe contain almost all the matter that's in the universe, which is really kind of surprising for folks when they first comprehend that, because you go, well, this isn't what we're not used to. Everything we encounter on the Earth is not what the stars are made of. The stars, essentially, the majority of the mass consists of 2 elements, hydrogen and helium, as you probably know. But other than your party balloons, you probably don't have much of a daily encounter with either one of these elements. So what was so important about this total eclipse of 1868? Well, what was important was a whole bunch of different discoveries were sort of coming together about at that time, including the invention of the visible light spectrometer, which had occurred a few decades earlier. But what was becoming clear by this time is scientists and chemists were actually noticing that elements had unique emission spectra. And the problem was, and they were noticing that some of these emission spectra were present in the emission of light from stars, because they had a spectrometer now that could separate the light into these wavelengths. And we really got interested, folks really got interested in the idea that they could discern what elements were present in those stars, as Sylvie showed earlier, just by looking at those spectra. However, the problem was, if you might have noticed in Sylvie's presentation, there's this overarching background that's in the visible region that's really just black body radiation. It's thermal radiation that's continual, and it sort of masks the elemental composition or the individual fingerprints of those elements, the emission lines of those elements. And when you look at the sun on a non-eclipse day, it's so overwhelming, the intensity of all these other broad spectra, that you can't actually discover the elements present there. So what they realized, these British scientists realized, is it might be good to look at the sun during a time when the intensity was greatly attenuated. And it turned out that sort of realization happened at this eclipse in 1868. So that happened in southeastern India. part of British India at that time. So these British astronomers, a whole lot of astronomers, but British astronomers particularly that it's credited for historically, were Norman Lockyer and a group of other British astronomers traveled to southeastern India. And they noticed if you sort of resolve down in the background of these spectra, you can see this continual color wavelength from red to violet. However, in there, you could actually see these individual discrete lines. And they realized that there was this yellow line that was present in the emission spectra. That works. There's this yellow line present in the emission spectra of our sun that was very close to these D1 and D2 emission lines of sodium that you also saw in Sylvie's slides earlier that she witnessed recently. But the more they looked at this, it took them months to really think about this, and it turns out it might be ascribed to the wrong individual. It was actually a routine astronomer that may have actually made this kind of a less known astronomer in one of the physical laboratories in India that might have actually made this distinction, that this was not the same as these two lines. And they actually concluded that this might be a new element that wasn't even known on the Earth. And up to that point, every element that was discovered on stars like our sun had already been known on the Earth, like hydrogen and sodium. And hydrogen was really clearly was there in our sun, but this one wasn't so clear. So this was a point of contention for many years, whether this was actually a new element that was responsible for this, or was this actually just some kind of hiccup in the apparatus. Oops. So Norman Lockyer, by the way, is also famous for something else. He was actually the first editor of the very influential journal that many of you might be aware of, Nature. He was the founding editor of that journal, by the way, and actually was one of the founders of the field of archaeoastronomy and understanding that temples and pyramids may have some kind of astronomy relevance. So helium, as it turns out, as we know today, is the second most important element in the universe, and mostly in stars. And I wanted to point out that it's also most of the gas planets in our solar system, that would be Jupiter and Saturn largely, are composed of exactly the same elements for the most part, mostly hydrogen and helium. And they're actually thought to be failed stars because they never really achieved the mass. They'd have to be about 10 times bigger yet to achieve the gravitational force to actually get the forces necessary for nuclear fusion of hydrogen. And so quite interesting sort of perspective. So it really shows you how large stars are. Not only the concept that it's 99.9% of the mass in the universe, but they're so massive that the gravitational force will actually force atoms of hydrogen together to make helium, as it turns out. So just take a step back for a second. I wanted to relate something historically kind of interesting here. Who discovered or invented the visible light spectrometer? Isaac Newton sort of first came up with this idea that light was composed of component wavelengths ranging that our eye perceives as anything from red to violet back in the late 1600s. But it took a lot longer till almost the 1800s until a big improvement was made, and that was with the discovery or the invention of the diffraction grating. And that's basically finely resolved slits, as you see over there on the right side of the slide. This is a diffraction grating. Those slits, the distance between those slits is on the same order as the wavelength of light itself, about a micron and smaller. So they're very finely divided slits. And Rittenhouse actually first discovered this in Philadelphia, actually in 1785. He discovered this phenomena, but never really recognized the importance of the application of it. And actually Joseph Fraunhofer in Bavaria actually sort of optimized this and actually realized its application in astronomy. It's a little bit about that Rittenhouse grating. So it was actually discovered by, the concept was discovered by a lesser-known signer of the Declaration of Independence, Francis Hawkinson. When he was looking through a silk handkerchief, he realized that there was kind of an unusual diffraction of light through those finely divided fibers. And he relayed that to his friend David Rittenhouse here in Philly. And he actually recapitulated that by taking hairs and stringing them close together at different widths in a planar apparatus, and actually noted that if he changed the distance between those fibers, he got different angles of diffraction of light, which was really interesting. But as far as the historical accounts suggest, neither of these guys actually pursued this and really understood that it may have a practical application, and that really was Fraunhofer in Bavaria actually was responsible for that. And Fraunhofer is really the father of the whole idea of visible light spectrometry, especially as it relates to astronomy. So today it's sort of a modern double grating spectrometer. You can actually get these types of two-dimensional spectra where you've separated both by visible light, the visible spectrum, but further you can resolve all these dark lines you see. These are now known as Fraunhofer lines. Those are actually the absorption spectra of all the elements in our sun, for example. This is off a NASA site. You can actually see these are fingerprints for the electronic transitions in those elements that are present in our sun. And there's a lot of elements in our sun other than hydrogen and helium. They're minor, but their signature is there, and you can look at other stars as well to see these same signatures. But you need a very sensitive instrument too, because the levels of some of these are very low compared to hydrogen and helium. So today we actually we know this is sort of the periodic table of the emission spectra of all the elements in our periodic chart. Not showing up too well here, but you can actually see the individual emission lines. Our eyes, of course, would see these as a composite if we looked at the emission, the light emitted from a star that had these. We would see it as a composite of all these colors. But if you use a grating and you separate the wavelengths, you'll see the these fingerprints, and you can identify each one of them by that fingerprint. So what's really kind of curious about this is it took almost 30 years from the time that this was discovered on the sun, helium, until Ramsay in Scotland actually discovered the element helium on the Earth. So this is the only element that was ever discovered elsewhere in the universe before it was discovered on the Earth, the only one. And Ramsay was actually the one who discovered all the noble gases, by the way, in Scotland. Very, very good chemist. But the way he discovered helium is kind of curious. He wasn't looking for it. He was dissolving uranium ore, which was common back then. You could dissolve rocks by putting them in acid. And he actually saw the evolution of a gas from it. And he was curious enough to actually look at the emission spectra of that gas. And he curiously looked closely, and he noticed that it matched this yellow emission line, this D3 emission line that had been earlier reported in our sun. And he went, wow, maybe that is an element. So that's kind of cool. It was very controversial for that whole 30 years. Was that really an element? But that unraveled a whole bunch, everything essential to astrophysics that unraveled is the understanding that, yes, there was hydrogen and helium in our sun. There was helium on the Earth. This was really an element. It was really kind of incredible what that led to after that. But in the meantime, what was another sort of curious phenomenon was, where might this element be present on Earth? It's really rare on the Earth. Anybody aware of where it is? It actually was discovered out in Kansas about 1905, that certain natural gas wells were inflammable. The gas that came out of them were inflammable. And it turns out about 10% of that is helium in those gas wells, as it turns out. It's kind of a long story. But all of our commercial production of helium now comes from the extraction from natural gas from gas wells out in the western states. And it actually doesn't derive from nuclear fusion. It actually derives from the alpha decay of uranium, thorium, and other alpha decaying isotopes. So it's kind of a different source on the Earth than it was on our stars. Get this straight. So curiously, it took a little bit longer, though, for folks to actually find this on stars other than our sun. So this French astronomer took, I think it was 1876 that he actually discovered it in a star in the Cygnus constellation. Curiously, it's most of the important discoveries early on in stars actually came out of investigations of the Cygnus constellation, by the way. It's kind of curious. So it took almost another 50 years for really this whole story to come together. For many decades, folks thought that, okay, there's hydrogen and helium in the stars, that's two elements in the stars, but they didn't really know what the significance of that was. But for years, people wondered, what is the source of that energy that we're so fascinated to look at? What's the source of that enormous energy? And people refer to it as hydrogen burning. So they thought of it as like hydrogen combustion, but of course there's no oxygen in there. So where was this coming from? So it really wasn't until 1920 that Arthur Eddington actually was able to correctly speculate, and then eventually others were able to prove that the source of the energy in the stars was actually a fusion reaction of our simplest element, hydrogen. The gravitational force being so great that the nuclei are actually forced together in this really dense plasma state of hydrogen that exists in the stars. In the process, enormous amounts of energy are released. Well, I can't get this clicker straight either. So this is the part of the story that I became familiar with when I worked at the Department of Energy. As you know, you kind of work with old timers when you're kind of a youngster there. And I actually worked with someone who actually knew Hans Bethe. Hans Bethe made the most important contribution to this field by unraveling the actual nature of the fusion reactions that are occurring in stars. By the way, any of you who saw the Oppenheimer movie, he was one of the folks in the Manhattan Project featured in that movie. Hans was curiously always philosophically against the development of the hydrogen bomb. Yet curiously, or ironically, most of his work was needed for the development of the hydrogen bomb. So it's kind of a deep irony that he was a German turned American physicist that actually was largely responsible for actually our ability to recapitulate fusion reactions in actual physical laboratories on the Earth, which of course is really a big part of the story of what the Department of Energy is finally able to achieve these days. So the last thing I wanted to talk about in this story was, helium's a really abundant element, we believe, in all stars, but it actually, it's also believed to probably be important in a lot of the gas planets, exoplanets outside our solar system. But it wasn't this was a story that came to my attention back in 2018. It wasn't until 2018 that helium was actually discovered in the atmosphere of an exoplanet. And so this was actually the first discovery. And by the way, I wanted to highlight here that this was in a shell spectrograph, pretty much like the one I talked about earlier, kind of a sequence of graph of gratings. By the way, I looked for where this exoplanet is. It's interestingly in the same constellation as Cygnus. If you look on Stellarium and look at where all the known exoplanets are, the greatest concentration of them are in the Cygnus constellation, of course, because we're looking towards the sort of Milky Way center. But I thought it was curious that there's such a great concentration of identified exoplanets right there. So anyway, in the atmosphere of this planet, helium. This is actually mostly helium in the atmosphere of this planet, and it also sort of expands and contracts much the way we heard about earlier. They believe. switch. So a couple things I'd recommend. I think this is really interesting. The sort of real old history of this as it relates to astronomy and some of these astrophysics and astrochemistry discoveries. This is a sort of a free book that actually was first written in 1906. It's now freely available, and so if you want to download it, it's really interesting. And this book here really accounts for a lot of the things I've told you that I learned otherwise through working at the Department of Energy, that parts of the story that I've talked about tonight. So I think I'll close that with close there. Any questions about anything that I talked about there?
Well, a little bit confusing. When you said the stars represent 90% of the mass of the universe, I presume you're talking about visible, not dark matter.
Yeah, we're not talking about dark matter.
Baryonic mass.
Right. Of course, we don't know what dark matter is, so it's hard to talk about.
Right.
It's become popular to have helium balloons at every birthday party and every thing you can think of, dark. And then that helium is released and gone forever. Is our production of helium able to keep up with that?
It's actually quite a reserve. There's quite a reserve. So the question was, are we wasting helium? And it is limited. There's quite a reserve. The importance of helium is it's being used as a cryogenic agent for MRI machines. And by the way, working in the superconducting field that I originally did, in order to get to superconducting magnetic temperatures, most of the current materials require liquid helium temperature, so something around 7 Kelvin, basically. So it's really important that we have that as a cryo agent. In fact, all of the rockets, we use that as a pre-coolant prior to loading liquid oxygen to pre-cool everything and to flush everything prior to putting liquid oxygen. So it's used for a lot of important things, including medicine now, And so, yeah, I think we are wasting it. But on the other hand, I always talk about this when we talk down at NASA at the visitor center. And a lot of the younger people will say, well, why don't we just extract it from stars? It's 30% of the star, right? So I thought, well, yeah, it's in a plasma state in the stars. And so you could probably use some kind of magnetic field to pull it out. So, yeah, there's some interesting ideas about where else you'd get it from. But, yeah, it's quite limited. It's really only in the gas well deposits out in the Western states and Europe.
So is that yes or no? Are we?
Yeah, we're wasting it
faster than we're.
I really don't know. I mean, a few years ago there was a lot of concern about it. Now that there's other wells opening up, and I think Spain has one now that's the main source. There's been less concern. For a while, we were kind of at a pinch because of the use of U.S. helium. I really don't know for sure how close we are to the end of that.
It's more expensive than balloons, if that's any.
Yeah, I think it's definitely more expensive. Yeah, but yeah, like anything else, this is a limited resource and it's not being regenerated. So, but like you said, it's a very light gas and it floats off into space and you don't have it anymore. But maybe it'll create a new planet. You never know. Okay.
Shall we do the next one?
Yeah, I guess what I wanted to do is share with you kind of the educational outreach, kind of what we did the other night at the library. And I think it's a great example of what we could do as a group to kind of get younger people excited about astronomy, as many of us got excited about the field when we were younger. Let's see, can we use that big mic for that?
Yeah.
I got it. Okay, I'll just transform. So this has kind of got a musical background, and I like to do this at NASA because we call them hyperlapse tours. It kind of captures the attention with both sort of pictures and music. And I think for younger people that are used to kind of instant gratification, that's important. Oops. Sorry.
I think that's fine.
That's it. Thank you all.
I don't know where it went. Do you need your presentation back?
No, you can.
There you go.
Sorry about that. Okay. Well, that concludes tonight's meeting. I want to thank all the presenters and Louis and John for helping out with all the AV stuff, and George taking notes over there for Jeremy, and and have a good night. And you can hang around a little bit and talk if you want, socialize, and I'll see you next month at the auction. Take care.
Great talk.
It's large.
So stop the stream, right?
Yeah, stop streaming and then wait 30 seconds.